Ions. In this lesson, we're talking about subatomic particles, what's inside the atom, atoms and ions, knowing the charge, Bohr-Rutherford ion diagrams, multivalent ions, naming and formula writing, and rules of ions. Ions. So in this example, we need to assume that red and green are opposite. You can see that they're on opposite ends of the color wheel. So they're opposites, and they're going to cancel each other out. Therefore, the net color is going to be neutral because there's an equal number of red and green circles in our diagram here. We have 5 red, 5 green, therefore we get a neutral object. Now, if we take away 1 red, our net color will be green. So you can see now we have 5 green, 4 red, so we're going to be plus 1 in the green section. If we take away 2 red, now we have 3 red and 5 green, and we're going to be plus 2 in the green section. Now, what's our net color here? Well, we're going to have 2 red, 5 green. So we're going to have a net color of 3 green. Now, this is going to be important in a moment. How about now? Well, if we count our reds, we have 1, 2, 3, 4, 5, 6, 7 reds, and we have 1, 2, 3, 4, 5 green. So now we're going to have a net plus 2 on the red side. So now in this arrangement, the green are going to be trapped inside, and only the red can be added or taken away. Now if we take away 2 red, we're going to have 1, 2, 3 red, and we're going to have 5 green. So we're going to have a net color of plus 2 green. Now in this case, we have 1, 2, 3, 4, 5, 6, 7 red, and we're going to have 5 green. So now we're going to have a net color of 2 red. Similar in this case. We took away 2 red, now our net color is 3 green. So what I hope you can take away from these examples is that when we take away or add different colors, we're going to get a net of the other color. And that's going to be very important when we're going to be talking about our ions. So what does this have to do with chemistry? Well, if we recall our subatomic particles, we have electrons, protons, and neutrons. In our example, our electrons are going to be the red, and they're going to be negative, and our protons are going to be the green, and they're going to be positive. Atoms are composed of all three, but when we're talking about ions, we're only concerned with electrons and protons. So since electrons and protons are oppositely charged, they cancel each other out. When they cancel out evenly within an atom, the net charge is 0, and we say the atom is neutral. In an atom, protons, the green, are in the center, and the electrons, the red, are on the outside. And only our electrons can be added or taken away, just like our previous example. This atom has 4 protons and 4 electrons. You can count them. 1, 2, 3, 4 electrons, 1, 2, 3, 4 protons. It has 4 positive and 4 negative charges, therefore. Since the charge is equal, they cancel out, and the atom has a net neutral charge. You can say that there's plus 4, and then we're going to add negative 4. Plus 4 plus negative 4 is equal to 0. To find the net charge, we add the number of positive charges and the number of negative charges. Make sure you don't change the sign. So in this case here, we're only going to have 1, 2, 3 negatives. So that's our plus negative 3. And we're going to have 1, 2, 3, 4 positives. That's our plus 4. So plus 4 plus negative 3 gives us an overall charge of plus 1. This atom in particular is charged plus 1. Check your understanding. So to find the overall charge, we're going to take our plus 4, because that's how many positive charges there are. We're going to add negative 2, because there's 2 negative charges. Plus 4 plus negative 2 is plus 2. So this atom has an overall charge of plus 2. Check your understanding. Find the net charge. So we have 1, 2, 3, 4, 5 negatives. So we're going to add negative 5. And we have 1, 2, 3, 4 positives. So plus 4 plus negative 5 is equal to negative 1. So this atom has an overall charge of negative 1. Check your understanding. Find the net charge. So in this case, we have 1, 2, 3, 4, 5, 6 electrons. So we're going to add negative 6. And we have 1, 2, 3, 4 protons. So plus 4. So it's plus 4 plus negative 6 gives us an overall charge of negative 2. Ions. When adding electrons, the atom will gain a negative charge and become negative. We are becoming more negative as we are adding negative charges. When removing electrons, the atom becomes less negative. It loses its negative charge and becomes positive. So in this case, we've lost 1 negative, and now our overall charge is plus 1. Atoms and ions. Atoms without a charge are called atoms. Atoms with a positive charge or a negative charge are called ions. The number of protons stays the same, only the number of electrons change. Ions. If an ion loses 1 or more electrons, it becomes positive and is called a cation. If an ion gains 1 or more electrons, it becomes negative and is called an anion. So you can see in our positive up here, our sodium has 11 protons, 11 electrons. If it loses 1 of its electrons, it only has 10, it gains a positive charge, and it becomes a cation, a positive ion. Chlorine has 17 electrons. If it gains 1 electron, it's going to have a negative charge, and we're going to call it an anion. How do we know what charge the ion will have? We need to look at the Bohr-Rutherford diagram. Most atoms will form ions to complete their outer orbit. Keep in mind that outer orbit electrons are called valence electrons, so we may use that term throughout the rest of the lesson. To be stable, atoms need a full outer orbit with either 2 or 8 electrons, so they can be like the noble gases. The only one that's going to have 2 is going to be our helium and our hydrogen. Those are the only 2 atoms that can have 2 electrons in their outer orbit, all the other atoms are going to have 8. And in our diagrams, we're going to show our electrons as our X, but many appear to circle. So if you see it in textbooks, you may see an atom with a circle around the outside. That's fine as well. I just show them as X's because I feel it's easier to pick them out. So let's look at a few examples. So sodium is drawn here. That's the Bohr-Rutherford diagram for sodium. You can see it has one electron in its outer orbit. This sodium is going to lose its one valence electron and become Na+, like we see right there. Notice that Na+ has the same configuration as the neon. So you can see that these two guys have the same electron configuration. Neon is a noble gas, and that's the state that sodium wants to get to. And you can also notice that when it loses its outer orbit, the orbit is just gone. There's no such thing as an orbit if there's nothing to orbit inside that orbit. So once we lose that outer electron, that orbit disappears, and now sodium has a full outer orbit. Fluorine gains an electron to fill its outer orbit instead and becomes F negative. So you can see that's our regular F, that's our fluorine, and you can see it has one unpaired valence electron. In total, it has 7, but since it wants 8, it's going to gain an extra electron, so this other electron is going to come in, fill that spot. Fluorine becomes F negative because it gained an electron, and F negative, you'll notice, has the exact same configuration as neon as well, just like sodium. So both sodium and fluorine change their electron configuration to become like the noble gas neon. Neon is stable, and that's where it wants to be. Put simply, an atom wants to have a full outer orbit, 2 for hydrogen and helium, and 8 for all the other ones. To do this, they can either, number 1, lose one or more electrons, become a cation, and lose their outer orbit, or 2, gain one or more electrons, become an anion, and fill their outer orbit. So how do you know? It'll be whatever's easier. If it has 3 or less valence electrons, it will lose all the valence electrons and become a cation. I.e., if it has 1 valence electron, it will lose 1 and lose its outer orbit, as it's easier to lose 1 than gain 7. If it had 3, it would lose 3, as it's easier to lose 3 than gain 5. If it has 5 or more valence electrons, it will gain enough electrons to fill its outer orbit and become an anion. So if it has 7 valence electrons, it will gain 1 instead of losing 7. If it has 6, it'll gain 2 instead of losing 6. Generally speaking, elements on the left, so the metals, metalloids, and hydrogen, will lose their valence electron and form cations. That's going to be represented by our blue squares. Elements on the right will gain electrons and form ions, and that's represented by the red square. So there's a shortcut to figuring this out. So look at your periodic table. Ignore the transition metals. That's these guys here. The carbon family. That's these guys. And boron. That's that guy right there. Over top of the groups, write how many electrons they will lose or gain to have a complete outer orbit. 8 total, or 2 for hydrogen. Write whether it'll lose electrons, positive, or gain, negative. Remember, gaining electrons gives a negative charge because it becomes more negative. So for example, beryllium, Be, will lose 2 to shed its outer orbit and become Be2+. So looking at our periodic table, we're going to write right on the top, +1, +2. We're going to skip the transition metals. We're going to write +3, but we're going to ignore boron. Boron is not going to be included in our calculations. We're going to skip carbon, and then we're going to go -3, -2, -1. So +1, +2, +3, -3, -2, -1, keeping in mind which ones we're going to skip. If you can remember that, then you'll be good. How do we draw Bohr-Rutherford diagrams for ions? Well, number 1 is we're going to draw a regular Bohr-Rutherford diagram. Number 2 is we're going to include the protons and neutrons in the nucleus. Number 3, we're going to put square brackets around the diagram. And then number 4, we're going to put the charge in the top right-hand corner. If it's +1 or -1, we're just going to write the symbol. We're going to omit the 1. Naming ions, positive ions. The name is the same as the name of the element followed by ion. So for example, Na+ is sodium ion. Ca2+ is calcium ion. For negative ions, the name is determined by removing the end and adding IDE. O2 negative is an oxygen ion, which we call an oxide ion. P3 negative is a phosphorus ion, but it's called a phosphide ion. It's not as hard as you might think. It's the name that will make sense. Oxygenide doesn't make sense. Phosphoruside doesn't make sense. But phosphide sounds correct. Oxide sounds correct. If you look at the periodic table and go through all the ones that become anions, you'll find that it's a pretty easy process to figure out what the name will actually be. Things that are a little bit more complicated when we're talking about multivalent ions, they're mostly going to involve our transition metals, our copper, iron, gold, but also includes tin, lead, as well as a few others. The thing that's most complicated about them is that they have multiple charges, and you need more information. We can differentiate one version of the ion from another using Roman numerals. The Roman numeral represents the charge. Multivalent ions include the name followed by the Roman numeral in brackets. So for instance, copper 4+ becomes copper 4 ion. Ni3+ becomes nickel 3 ion. We can see the 3 is represented by the Roman numeral 3. The 4 is represented by the Roman numeral 4. Note, the charge on multivalent ions is always positive, and this is because of the nature of the atom involved. They are always going to lose their electrons, so they're always going to be positive, so you don't need to worry about that. There's never going to be an IDE at the end, because they're always going to be positive, and therefore we're going to name them like positive ions. The other thing you need to keep in mind are the Roman numerals we'll be using, 1 all the way to 7, so make sure you remember those. Multivalent ions, formulas. The Roman numeral in the name represents the charge on the ion. So lead 4 ion, that 4 becomes up here. Remember we said they're all positive, so it's always going to be plus. Cobalt 2, that 2 goes up here, and it becomes +2. So So you're going to write the element symbol, given the name, then write the charge using the Roman numeral, and keeping in mind that multivalent ions are always going to be positive. So how do ions impact you? Well, ions make up the salt you put on your food. Ions are required for your brain to function. They keep you alive by controlling your pH, and they allow you to move by controlling muscle contraction. Ions are also called electrolytes and are found in many sports drinks. Now, before you conclude the lesson, I want you to pause and watch number 1. And that concludes our lesson on ions.